Are you sure you put that in the right, the black one?
It was there like that.
Okay.
It's supposed to be in HDMI in or out.
I have no idea. First, I also have.
Alright, let's get started. We're starting a brand new topic today. Just a couple of announcements. So, homework 4 is on Canvas. Hope, those two rectangles that overlap?
Overlapping, yeah.
Right.
This dimension is getting very big. It's starting to count over definitely, I think it's bigger than 6 and then going 8 or 9.
8 or 9? I need you remember? Is that a yes? Is that a, you don't know? I don't remember.
I just asked it.
I have to think about this. It's been a while since I solved that problem, but I don't remember it being so big.
Yeah, it's been pretty big.
Anyone else see something like that? Is
Yeah,
that
but I think I'm doing it wrong, so I have the same question.
okay, you know what? I'll work out the details. And can you post a message on the corresponding
Somebody posted it last week.
last week?
Yeah,
We got
Friday.
it.
Okay. All right. I'll respond to that right after class.
Yeah,
Okay. Yeah, I don't remember that it should be that big, but
Yeah, only now.
okay. If I don't want you to be enumerating, up to 100 and then saying that okay, 100 works, but 101 does not work, so we see dimensions 100. That's a waste of a lot of people's time, and so I'll verify and correct it if necessary. Any other thoughts?
To prove something's packed winnable, would you recommend, should we go to the definition of packed winnability?
No. So you use these theorems that we've got in the class. So to prove, say for example, that some concept class is packed learnable, first of all you need to categorize that concept class. Usually the statement is the concept class is packed learnable using a particular hypothesis class. If the hypothesis class is not specified, you can assume that the concept class is the hypothesis class. And then you need to put yourself, see which bucket the question falls into. If the concept class is the hypothesis class and it is finite, the hypothesis class is finite, then you essentially need to see whether the log of the size of the hypothesis class is polynomial in the dimensionality. If the hypothesis class is infinite, then you need to see if the VC dimension is polynomial, is finite, not polynomial, it's finite. Literally that's it. Essentially, these questions are asking you to prove that, or to verify whether if for a finite hypothesis class, the number of functions is the log of the number of functions is polynomial. If the function class is infinite, then it's asking you to see if the VC dimension is finite. That's all there is. Yeah. Yes?
So there's a problem with a PC packed ability.
Right.
The singleton functions.
Right.
The x is a discrete instance space. Is it a finite or?
Yes, discrete implies, yes, in this case it's finite.
It's finite. Okay.
Any other thoughts? Yeah, you're right. I mean, it could be discrete and
Yeah, integers.
yeah. In fact, now you've reminded me, that would make an interesting question. But yeah. So the nice thing about this whole set of this kind of problem, this area, is that it's easy to invent questions, and many of these answers end up basically solving little puzzles. Involve solving little puzzles. So think of this entire homework as this collection of puzzles that you need to solve. That's how I would approach it. Let me give you some more details about your project. Hopefully all of you have feedback about your projects right now. Is there anyone here who does not yet have feedback? I think I've got through everyone. So at this point, I hope you're all working on your project. So I have moved the status date for the intermediate report by a week, so now they are due on November 16th. In fact, I've rearranged all the due dates. Please take a look on the class website. So the one that's immediately relevant to you is the intermediate status report. And here's what I expect. If you're doing a regular project, and that's about slightly less than half the class, you should tell me what your progress is so far. And many of you who are working on this are doing something that involves collecting some data and running some learning. And your intermediate status report cannot be, we have the data. You need to tell me what your data looks like. You need to tell me, say, give me some statistics about your data. Hopefully you should also have some sort of a baseline classifier set up. Something that says, here is a simple classifier and here is how well it does. Here is what the majority class is, and here's what the performance of a classifier that always picks the majority label is, and so on. It should detail the plans for the rest of your semester. It is shocking how quickly the end of the semester is creeping up on us, so please plan accordingly. And anything that you may have read, any cite some references and so on. If you're doing an exploratory project, by the time that date shows up, you should have submitted 2 different runs to Kaggle. And keep in mind that I expect you to, these runs should be algorithms that we have seen in class. I expect you to use your own implementations. Of course, there are many, machine learning libraries available out there, but that's not the point of the class. This is not a machine learning libraries class. In addition to that, you should also submit a report to Kaggle, to Canvas, where you have to your report should describe what you did, any pre-processing that you've done, feature transformations that you may have applied that seem successful. Describe something that may not work. Hold on. And also, once again, you have to describe what you plan for the rest of the semester. Remember that by the end of the semester, if you're doing the exploratory project, you should have submitted 6 different runs to Kaggle and tried out different algorithms. Yes?
Are those switched? The exploratory?
Oh, you're right.
Yeah.
So this is not exploratory. This is yes. This is what happens if you make slides at 2 a.m. General life advice: don't do that. All right. One more exciting announcement. Any questions about this before? Yes.
So can we implement bagging or something?
Yes, you can. So right now, let's enumerate the algorithms that you should be able to, in theory, implement. You should be able to do, you probably already have decision trees and perceptron. You have bagging, boosting, random forests. You can do some sort of an ensemble. Remember that bagging really does not, by definition, at least the version we saw in class, does not say whether it's bagged, what the underlying classifiers are, so you can now combine these things and get different variations. Already you have more than 6 different learning algorithms. Yes, there was a question.
You said 2 different runs?
Yes, 2 different algorithms. Okay, yes. Yes. All right. Enough copy editing of my slides. This is the exciting announcement. There's going to be a fun talk tomorrow. This is part of a lecture series that we are organizing over the year called Bytes to Stars, or Stars to Bytes, that tries to combine data science and astronomy, and we are inviting people in this intersection. Tomorrow we are going to have someone from Utah, Kerry Wagstaff. She did her undergraduate degree here, right here in the School of Computing, a while back, and then went on to do a PhD in machine learning, and then joined NASA's Jet Propulsion Lab, and she works on applying machine learning to data that is collected from all these space probes. Her talk is going to be at 2 p.m. tomorrow. She tried to show up. Interestingly, one of the things I noticed in her abstract is she's going to talk about how random forests work in this data. So maybe it would be an interesting I don't know what exactly he's going to say, but hopefully you should be able to follow. So, do show up. All right. Let's actually start with the real part of the class. Today, we're going to start looking at support vector machines. All right. So let's start with a new topic today. It's going to be support vector machines. And just to take stock of where we are, we've seen a bunch of learning algorithms. I just enumerated a few more than what's written here. And Perceptron produces a linear classifier, and in fact, AdaBoost also produces a linear classifier. I want you to think about why AdaBoost produces a linear classifier. We've also seen a bunch of general learning principles. We've seen what overfitting is, we've seen mistake bound learning, pack learning, sample complexity, the importance of the choice of a hypothesis space. We've seen what VC dimensions are, the different kinds of error. Training error is simply the error on a particular training set. And the really important point of learning is generalization. So we also saw what generalization errors are. And coming up over at least today and the next lecture is how we can directly apply these lessons from learning theory to derive a general principle for learning, which involves learning by minimizing loss or risk. And this idea, minimizing risk, is the dominant strategy for generating learning algorithms today. So going ahead, if you, for example, want to use a fancy new hypothesis space with a certain neural network architecture that has never been seen before, and now you want to derive a learning algorithm for this new hypothesis space, it turns out you can plug that hypothesis space into this recipe for risk minimization and derive a learning algorithm. And in fact, what is even more amazing is you don't have to derive the learning algorithm. There are software libraries that will do the calculus for you and create a learning algorithm for you. And we'll see how that will build up to that. So for example, you may have heard of TensorFlow. That's what it does. It automatically does the calculus for you and creates a learning algorithm for a new neural network that you may define. And we're going to start off with baby steps. We're going to still continue looking at linear models. We've already seen linear models, and we've also, the whole class is arranged around this idea of how do I know whether a learning algorithm is good. When we combined online learning with linear models, we saw Perceptron, we did not see Winnow, but there are some slides on the class website. If you want, you can take a look. It's a variant of it's another online learning algorithm that uses a multiplicative update. We also saw pack learning and agnostic learning, and when we merge linear models with essentially pack, the theory from pack, we get what is called a support vector machine. We'll also see another way to ask the same question or answer the same question of how good is my learning algorithm, and that's Bayesian learning, and we'll start Bayesian learning very soon, maybe in a couple of weeks. And it turns out that merging Bayesian learning with linear models gives us logistic regression and naive Bayes. We'll get to that hopefully before the end of the semester. Alright, so let's start. By the way, is everyone okay with where we are in the big picture? Any questions? Yes?
Yeah, so when we talked about AdaBoost, there was one step in the algorithm that was left rather nebulous, which is find a hypothesis at iteration t that minimizes the weighted error. Yes.
Right? In fact, I deliberately left that nebulous. Once we cover the risk minimization principle, you'll be able to essentially plug in this idea to get a hypothesis that minimizes error. It will work for things like Perceptron, it will work for SVMs, logistic regression and all those. So one place where it won't directly fit in is decision trees. For decision trees, the way to think about it is, so the question was, how do I find a weighted, in the specific instance of the question in decision trees becomes, how do I find a decision tree that tries to minimize the weighted error? where weights are where every example has some weight. And if the weight is high, I want to make that more correct. ID3, for example, does not take into account any weights. The way to modify this is to use the weights to redefine the probabilities that are used to compute the entropy. So the entropy changes to favor examples that have high weights. I'll let you think about that, and it's not a terribly complicated change, but you have to kind of think about what's going on. The default version of entropy that we have essentially uses the idea that all examples are equally weighted. And the way to think about that is entropy is defined over the labels, right? How do you know what is so in order to define entropy, you need the probability of plus and probability of minus, for example. Probability of plus is computed by counting the number of pluses and divided by counting the number of examples. Instead of counting the number of pluses, you add up the weights. And that way, an example with a higher weight automatically gets a higher importance. I'll let you derive that and we can iterate that. You had the same question also, so hopefully this gets fixed. And for all the other classes of algorithms, this idea of risk minimization will be directly applied. Alright, so this lecture is split into, or this topic is split into multiple lectures. Today my hope is to introduce you to this idea of training by maximizing margin, and then introduce the SVM objective. In the next lecture on Tuesday, I'll talk about how we can solve the SVM optimization problem and introduce the general risk minimization principle. I'm going to delay the idea of kernels and support vectors to a little later in the semester because I want to move on to Bayesian learning. So let's talk about learning by maximizing the margin. So everyone knows this slide. Hopefully, if I wake you up in the middle of the night and demand what this, ask you to tell me what's here, probably all of you know this, right? Yeah, I know, even I can't. But we do know we do know how to interpret this. So the theorem, diagnostic learning theorem that involved VC dimension, essentially says if you have a collection of examples, you have a particular training set of m examples, and we want a classifier that makes low error, or rather we want the guarantee that with high probability we'll have a classifier that makes low error. Then we can say that the generalization error of the classifier that's trained on the data is upper bounded by the training error, and a big term that for the purposes of this discussion involves the VC dimension. More importantly, as VC dimension gets lower, this bound gets tighter, right? So instead of just instead of just finding a hypothesis that has a low training error, our goal should be to find a hypothesis that has low training error plus something that involves a VC dimension. Does that seem like a reasonable idea? That way you get a tight approximation of the generalization error, and that way we are essentially minimizing a good surrogate of the generalization error. Okay, now let's see how this applies to linear classifiers. What is the VC dimension of a linear classifier in D dimensions? It's D plus 1. Okay, so if the given a data set and you have D features, all linear classifiers have the same VC dimension. So there's some VC dimension of a linear classifier in D dimensions is D plus 1. If every linear classifier has the same VC dimension, this term is a constant. So something's weird. But actually that's not quite right, and that's this style of reasoning will is the incongruence clear? Does that make sense? On one hand, we want to minimize, or a good a promising idea seems to be minimize the sum of the training error plus this function of VC dimension. Find a linear classifier that minimizes these two terms, the sum of these two things. On the other hand, the term inside the box here is the same for all linear classifiers of fixed dimensionality. So there's no point in adding the term because it's going to get, it does not change by picking two different linear classifiers. So how do we go about it? It turns out that all linear classifiers, even with the fixed dimensionality, are not the same. Let me, in order to think about that, we have to think about margin. So remember margin, this thing that we saw when we were talking about perceptron. The margin of a hyperplane, this hyperplane let's say, with respect to a data set is the distance of this hyperplane from the data point closest to it. So this is just a pictorial representation of the margin. You guys are all experts on this, you have seen this before. But let's think about it a bit more. Say I give you the same data set and give you two hyperplanes, H1 and H2. Using the margin, can you tell me which one's a better choice? Why?
It has a wider margin.
It has a wider margin, so why would that? But both of them perfectly classify the data. So why would a wider margin be a good thing? Since you seem very confident, I'm going to pick on you.
I wasn't that confident, but I'll give it a shot.
Yeah.
So a wider margin to me implies there's a greater likelihood that the line that we use to split it could have a small amount of error in one way, direction or another without changing the actual classification. That's my guess.
That's a good intuition. Yes.
Well, it's centered in between the positive and negative.
Why is that a good thing, other than this aesthetic sense?
Because my negatives are bound to be closer to the negatives.
Think about the following. I think you are essentially hitting on the right intuition, but in order to answer this question, yes,
It reduces the chance of overfitting
it reduces the chance of overfitting. Yes.
because you're training.
But neither of these are overfitting. Both of them are essentially perfect on the training set.
They're perfect on the training set, but we don't know how they are on the test set. So the more margin you have, the better they're going to likely to do on the test set.
That's right. One more and then I'll, yes.
Yeah, that's it. I was going to say, the training set just covers some of the distribution, so we're likely that some of the distribution might be outside of the training set, but it's going to be close to it, so the bigger the margin is sort of the better.
That's essentially the point. So let's say a new example comes in. That's not from the training set. If you pick a classifier that has a larger margin, you're more likely for that example, that new example would be on the right side of the margin. Because you have given yourself the biggest gap that you can possibly afford. Intuitively, most people would agree that larger margins are better. But that does not sit well with the idea of VC dimensions. Both these hyperplanes have the same VC dimension. In this case, it's a two-dimensional hyperplane. So the VC dimension of both these hyperplanes is, in this case line, the VC dimension of both these classifiers is 3. But somehow, H2 should be a better classifier than H1. So what we need, it tells us that our VC theory is inadequate. What we need is a new definition of VC dimension that somehow is data dependent. Well, the way to think about that, and this was the innovation that Vapnik introduced, is suppose we consider a hypothesis class of linear classifiers that have a particular margin. So say you have some number margin gamma 1, H1 is the set of and a particular data set. Suppose you have a data set and a particular margin gamma 1, and we consider the set of all linear classifiers that have margin gamma 1, and we consider another set of all linear classifiers that have a margin gamma 2, and let's say gamma 1 is larger. The entire set of functions with that larger margin is better in some sense. Right? Larger margins give you this more wiggle room. This intuition can be formalized into a theorem from Vapnik. Suppose you have a class of functions, a set of linear classifiers with a particular margin. Let's call this H, this set of functions, and let's say the margin is gamma. Then it turns out the VC dimension is not just d plus 1 for d dimensions, it's actually less than the minimum of r square over gamma square plus and d plus 1. This r square over gamma square is something that keeps coming up. We saw this in perceptron, it keeps coming up. This is a useful, and it's the same r that we saw in perceptron. So essentially what this says is, if you have two classifiers and one of them has a larger margin than the other, pick the one that has the larger margin because it reduces the VC dimension. Gamma gets smaller. This theorem essentially validates that intuition. Because lower VC dimension implies better generalization. Lower VC dimension implies better generalization, higher margin implies lower VC dimension. So here's the learning strategy. Find linear classifiers that have a higher margin. Questions? Yes?
Why exactly does higher margin imply lower VC dimension?
So what you need to, that's basically the proof of this theorem, but the intuition here is that there are fewer functions with larger margins. Right? So if I give you a data set, and let's say this way, let's make this a data set that looks like this. Now I can find multiple, let me just create a new slide. So I have pluses and minuses. I can now find, let's say I pick a particular margin. Let's say this is the margin, and here this is a particular linear classifier, and that's the margin. And let's call this gamma 1. There are many lines with the same, I can draw it this way, I can draw it this way, this is also gamma 1, let's say. There are many more lines with smaller margins than there are lines with larger margins, because there's lower wiggle room as you demand a larger margin. And that way, and that is the intuition that this hypothesis class should be small. And so the flow of argument here is, we know that it's a good idea to find a classifier that search in a hypothesis space that has lower VC dimension. Among linear classifiers that separate a data set, the one that has a higher margin has lower VC dimension. So let's now use this to define a learning principle. Find a linear classifier that separates the data, and find one that has the largest possible margin, because that will have the lowest possible VC dimension. So this gives us our new principle for learning. Yes?
So while the VC dimension will be
Can you speak up?
So while the special set will be smaller, take for example, if the positive ones are sort of more spread out than the negative ones, then you want a margin that's sort of focused more on the negatives and positives, because if it's straight in between, then it will be less accurate.
Right. So essentially the point that you're making here is, this does not account for the distribution of the positives and the negative within the positive and negatives.
Yeah.
It only accounts for the separator itself. It does not say anything about how the positives and negative points are internally distributed. And this difference is both a philosophical one and a practical one. This is essentially the difference between generative and discriminative classifiers. Discriminative classifiers are a family of classifiers that only say, I don't care about what's happening within each class, I only want to characterize the classifier itself. Generative learning is this idea of characterizing what's happening within each class. We'll get to the differences maybe in 3 lectures, 3-4 lectures. Alright, so the intuition is larger margin gives you lower VC dimension, lower VC dimension gives you a better generalization bound, so let's try to find classifiers that have a large margin. And that is going to be our learning strategy that defines what support vector machines are. So that is going to give us also the SVM objective. In order to derive the SVM objective, let's say that let's first revisit the geometry of a linear classifier so that we can kind of refresh the formal definition of what a margin is. So remember that for a linear classifier, in this case we have a linear classifier in 2 dimensions. The prediction is always the sign of a dot product. So we have a line, in this case it's B plus W transpose X, and let's say this side is the side where B plus W transpose X gets positive. The prediction is the sign of this dot product. Given a line and a data set, we can define the distance of the line from the data set, from any point. Let's call this point here x1, x2. The distance of this point is the absolute value of B plus W transpose X divided by the norm of W. This is, hopefully you've seen this, I don't know, in middle school or something, right? So you know what I'm talking about. So this is basically the distance between a line and a point. But an important degree of freedom that we have is we really don't care about the value of B plus W transpose X. All we want is the sign, right? This particular line here could have been B plus W1 x1 plus W2 x2 equals 0. It could have also been twice that. The parameters could have all doubled or multiplied by 1,000, as long as any positive scale does not make a difference to the sign of this, to the sign of the dot product. So we only care about the sign. I could have multiplied this distance by any number C, that's a positive number, and the prediction remains the same. And that's an important point that that's an important property that we'll exploit to derive the SVM objective. So remember that before we move on, I want you to kind of internalize this idea that we can multiply the distance, we can multiply the numbers that define the hyperplane by any positive number, and the sign of the dot product remains the same. Questions? If there are no questions, I'm going to just move on. Let's make this a little bit more formal. The distance between any point xi, so if you have a point xi, and x is a vector here, and a line that is defined by, say, W transpose X plus B equals 0 in high dimensions, in any dimensions, is simply the absolute value of W transpose X plus B divided by the norm of W. If I know that this point should be classified as, say, a positive, then if for example, let's say that this line perfectly classifies all points. If this point is a positively labeled point, let's call this yi equals plus, then this is simply, I know that W transpose X plus B is positive, right? Assuming that this line correctly classifies the data, then this is simply W transpose X plus B divided by the norm of W, right? If you have a negative point, let's call this one xj, and the label yj is minus, then this distance is minus W transpose X plus B divided by the norm of W, right? In both cases, the distance of the line can be written, from the point can be written by the product of yi times W transpose X plus B divided by the norm of W. the margin is the smallest such distance. Which means the margin can be formally defined to be the minimum value of yi times w transpose x plus b divided by norm of w. So far so good? So now we can start thinking about formalizing our learning principle. We want to find a weight vector w and actually a b also, so the maximization is over w and b. We want to find the w and the b that maximizes the margin. So we want to find a w and a b that maximizes this gamma, which in itself is the minimum value of the distance between the line and the point, the absolute value of the distance between the line and the point. This quantity is also called the geometric margin. Sometimes in the literature you will also see the phrase functional margin. The functional margin is simply the numerator here. It's a geometric margin of a weight vector of a classifier that has a unit unit norm parameter. So the norm of w is 1. So we want to find a classifier that has maximum gamma. But we only care about the sign. We don't care about the magnitude. As I said, I could have multiplied this by any positive number c. What we are going to do is we are going to pick a particular value of the positive number. Suppose we, in hindsight, found the weight vector and divide, let's say c equals 1 divided by the distance of the closest point. So let's say this distance, let's call this distance capital D. So let's say I say c equals 1 divided by capital D. In hindsight, I could have done that, and that's not going to change a thing right now. But if I knew that this point here was the closest point, then then the distance would become 1 divided by norm of w, the distance of that particular point, right? And we have the freedom, because we have the freedom to scale w up and down, that's what we're going to do. So instead of simply just maximizing the margin, what we're going to do is find the margin find the w that maximizes 1 over norm of w such that the closest point is at a distance 1. We're going to find a w that such that the closest point is at a distance 1 divided by the norm of w, and try to find the maximum margin. And these are equivalent. Questions?
What's equivalent?
Trying to find a w that maximizes the margin, and trying to find a w and b also, I'm assuming there's always a b, that has that maximizes 1 over the norm of w, this quantity here, subject to the condition that the closest point is at that distance. Such that the closest point has the b plus w1 x1 plus w2 x2 equals 1. That's the distance of the closest point. These two are equivalent. And the reason we are going through all these mathematical or essentially algebraic hurdles is because we want to set up an optimization problem that's easy to solve. And I have found that this particular point here tends to be a little bit unintuitive if you're seeing it for the first time. So what I encourage you to do is either ask me questions now or go back home, think about it, revisit this and try to internalize this idea. So I'll pause for questions. Yes?
So essentially what we're trying to do is, we are trying to model the distance between the line, the hyperplane and any of the points in terms of the distance between that plane and the closest point.
Exactly right. That's right. As a multiple of the distance between the hyperplane and the closest point. That's one way of thinking about it. Essentially what we are saying is, I want to find a line. Actually I probably have written it. So I want to, margin of w is the absolute value, or is min over x comma y in the data, y W transpose X. I'm ignoring the bias term divided by the norm of W. And the goal is find the W that maximizes margin. That was our original goal. Instead, what we are going to do is, which I'm going to write this explicitly, maximize W min over X comma Y, Y W transpose X divided by the norm of W. This is what we want to do. All I have done here is move this quantity into the margin. This is what we would like to do. But we have the degree of freedom that we can scale this up and down however we want. I'm going to say this is exactly the same as maximize W of C times some number C, I don't care what it is, min X to Y, the norm of W. As long as C is positive, life is good. In particular, I'm going to pick the value of C such that, suppose C equals it's 1 over. Something like this. The closest functional, 1 over the closest functional margins. If I can do this, then I can essentially cancel out that term. Cancel out the numerator, and I'm left with this quantity is max over W, 1 over the norm of W, such that Y W transpose X for the smallest one, min equals 1. If that condition is true, then I'm good. So, does this make sense? Okay, now we want to maximize the margin, and that's equivalent to maximizing 1 over norm of W if the closest point has a functional margin of 1. There's a question.
Why in the proof you made there's still an equality also when you add the C parameter?
Equality?
I mean, you add the C
Oh,
parameter.
it's the R max. I want to find R max, not the max, it's the R max. Yes, it's not. Yes. It's not an equality. Here it is. The R max is the same. Not the max, because if the maximum will get multiplied by multiplied or divided by C, depending on how. Yeah. That's right. That's a good point. I always forget to put R max. Okay, but we want to maximize 1 over norm of W. We are much better off instead of maximizing 1 over norm of W is the same as R min norm of W, which is the same as R min the square norm of W, or I can put a half if you want, but the square norm of W is exactly the half W transpose W. So what I want to do is, minimize the norm of W, but still we have that condition. We want the closest point such that the closest point is has a functional margin of 1. If the closest point has a functional margin of 1, every point has a functional margin of at least 1. Right? So this is a max margin classifier. This is the optimization problem that we've set up to train a max margin classifier. The objective of this function, this is called, so this is, how many people have seen convex optimization formally or at all? A very small number. So usually these kinds of problems are take the shape maximize or minimize. So let me just use a different new. So I want to minimize some. Let's say I have some variables. Let's call, and to make sure that there's no confusion with any of the notation we've used so far, I'm going to say theta are our collection of variables. Theta is some vector. I want to minimize the value of f of theta. I have some function, I don't know at this point what it is, such that some g of theta greater than or equal to 0. Some constraints hold. If f and g are both convex functions, and you know what convex functions are, or at least you've seen them before, this kind of a problem is called a convex optimization problem. Both f and g have to be convex for that. And the nice thing about convex optimization is that as a field, this has been studied extensively in mathematics, in operations research and such parts of math. The answer to this, let's call this theta star. Theta star would be the minimizer of the function among all values of theta where this condition holds. That's how to interpret this. That's how you should interpret this statement. If you like pictures more than equations, G could be any region in space. To make life easy, let's say it is some closed region in space. What this means is, inside this vaguely ball-like thing, the value of G is more than 0, which means this is called a feasible set, and our goal is to find a value of a theta. So this is, let's say, this region defines theta. Let's say it is two-dimensional, so theta 1, theta 2. But our search space is only inside the shaded region, and our goal is to find that particular value of theta where f of theta is the highest. Okay? This is the kind of proof by, not proof, but the intuition by Pitcher's version of convex optimization. The assumption here is both f and g have to be convex. Now, the reason I'm going through all this is because our learning problem is a convex optimization problem. We want to minimize the norm of w. The norm of w is a convex function, such that we have a whole bunch of constraints.
Excuse me?
Yes?
Why we need that to be equal or larger than 1? If we only care about the sign,
Because it's yi times w transpose xi, the closest point on either side is at least at a distance of more than 1 away from the line. That's what this is saying. So remember what we wanted. What we said was, for the closest point, y w transpose x should be equal to 1. This is how we derived this objective. If for the closest point y w transpose x is equal to 1, then for every point y w transpose x should be at least 1. So that's what it says. For all I enumerates over the data set that we have, yi w transpose xi should be greater than 1, and this condition ensures that every example has a functional margin of at least 1. And the equality holds for the point that's closest, the point that actually lies on the margin. This is a convex optimization problem because both the objective, the term on top, f is called the objective, and these are called the constraints. Both the objective and constraints are convex. Historically, this was called or at some point this became called the hard support vector machine. And it's hard not because it's difficult, but because it imposes a hard condition. We'll look at how to solve this optimization problem a little later. It turns out that there's been like a whole bunch of effort on solving such optimization problems. In particular, this class of optimization problems are called quadratic programming because the objective is a quadratic function and the constraints are in this case all linear. And historically what happened was, when this objective was defined, there was much joy and rejoicing because we know how to solve quadratic programs. We don't have to think about it, we can just make it somebody else's problem. It is the problem of the operations research community, and they have been working on this for 50 years, so they have built systems that can solve them. So all you have to do is take your problem, take your data set, write it down in this form, give it to a QP solver, a quadratic program solver, and we're done. So we basically make learning somebody else's problem. It turned out that was not the greatest idea, and we had to invent specific learning algorithms, specific optimization algorithms for this kind of a QP, and we'll see that in the next lecture. But there's a problem here. There's an issue here. Now, what happens if the data set is not linearly separable? Can someone tell me what happens if the data set is not linearly separable? Someone who's never spoken in class. What happens to the constraints if the data set is not linearly separable? You have spoken in class, but I'll let you talk.
So at least one of the points will not satisfy the YIW transpose.
That's right. If the data set is not linearly separable, consider something that looks like this. There is no line that separates the data, and there's no line that separates the pluses and the minuses. Alternatively, no matter how I place the line, let's say I put this line and I say this side is positive. There is, let's call this x1, y1, x2, y2, x3, y3, and x4, y4. If I draw a line, if I consider this particular w, then x3, for I equals 3, this constraint is not true. Because yi, w transpose xi, in this case is negative. Right? If the data set is not linearly separable, this is a test for linear separability, in fact. We want yi, if a data set is linearly separable, then yi, w transpose xi should be more than 1 for every point. There must be some w square that holds. And yes?
I still have a question about the bigger array program. One, where is the bias?
Oh, I'm assuming, okay, there's a bias. So all of this assumes that w contains a bias term.
But in the definition of the margin,
Oh, yeah. So there's, okay, now I see what the confusion is. There is an incongruence here. This should have been yi w transpose xi plus b greater than or equal to 1, and the corresponding objective minimize over w comma b, w transpose w plus b square. If you want, you can do that, or sometimes you drop the b, but essentially it turns out it does not make much of a difference. Let's just make our life simpler and put a plus half b transpose b. Let's just do this. But if I'm doing this, I could have just as well folded the w and the b together to create a n plus 1 dimensional vector. And if you do that, you get this. So I'm assuming the this w is not the same as that w. I see that, okay, I can't see that top thing in my display, that's why I got confused. So yes, the two w's are not exactly the same. Okay, that's a good catch, I should probably fix that. So if the data set is not linearly separable, what happens is one of the constraints does not get satisfied. And if you think of this in terms of the constraints defining the set of feasible w's over which this search happens, even if one of the constraints are not satisfied, then the feasible region becomes empty. There is no w that satisfies all these constraints. In other words, there is no w that will classify the data. In other words, this optimization program will fail. If we have a good version, a decent library that does the optimization and we are lucky, we'll get an exception. In general, so is the situation clear? Does this make sense? If you have this particular optimization problem and you get a data set that is not linearly separable, then we are stuck. We don't have a way of solving. Basically, we are just saying, can't learn. Any thoughts about how you might fix that? Let's say that you have a data set that looks like this. And you collected this data set by asking people to label things. And one of those people who labeled this thing, label your instances, was lazy and accidentally typed a plus. Would you say this data set is linearly separable? Oh, let's put a minus here, just so that I make it. No. The data set is not linearly separable. But if you kind of squint at this problem, could you, if I forced you to find a weight vector, could you find one? That was almost good enough. How would you do that? Can you describe that weight vector, and I'll draw it here? A vertical line, and let's say this side is positive. But would you be happy with that weight vector?
Yeah.
But why would you be happy? I mean, the data set is not linearly separable. What about this point here?
So now it's noise.
It's noise. Okay? But how do you know that's noise?
You told us.
I didn't tell you. Okay, in this case I give you that, I told you. But let's say you get a 1,000,000-dimensional data set and you know for sure that there is noise, you just don't know which points are noise.
You just find the error and it's just low. So just one of the points is.
But then you have to now, okay, let's say you have another point here that is a minus. Now you have to try all pairs of points. You have to decide which points are noise. If only something told you that these 2 points are noise, what you can do is just ignore them from the training and train your classifier. If you knew which points were noise, life would be good. Right? But we don't know that. It turns out we have a kind of a way to deal with that. The key idea is you don't demand that every point should lie outside the margin like we did before. We're going to allow some training points to break into the margin. And then we're going to penalize during optimization the number of points, or essentially the error, in some sense the slack, that we are allowing. We're going to demand that not too many points should be allowed to break into the margin, but if you feel like it's going to help things, allow some points to break into the margin. That's what we're going to try. So the margin, in this case, this margin, this particular data set, the separator has a large enough margin that would separate the points. So what we would do is automatically allow some points to break into the margin and ignore the ones that have done that in order to find a classifier that separates the rest of the points. That's what we're going to try. So this version of SVM is called the soft SVM. And actually, when people say SVM, the version that I'm going to introduce now is what they're talking about. And to derive that, we're going to start off with this formulation of the hard SVM that says maximize the margin such that every example has a functional margin of at least 1. Instead of that, we're going to introduce a slack variable, xi. This is the Greek letter xi, which I can type but I cannot write. So for future reference, I'm going to do this, and that means xi. I have tried hard mimicking the font and I cannot. So my squiggle is a xi. What we're going to do, what we're going to allow is we're going to allow every variable, every training example, a particular slack, psi I. And instead of demanding that every point should have a functional margin of 1, we're going to allow examples to have a functional margin of 1 minus psi I. But psi's are all positive. Okay? So that will give us a new optimization problem. The intuition here is the slack variables allow examples to break into the margin by an amount that is equal to psi. If the slack variables are all 0, then the data set is linearly separable. If all slack variables are 0. If for a particular example the corresponding slack is 0, then we don't need the slack because the point is anyway outside the margin. That's what we are going to, that's the interpretation that we will have on the side. This gives us a new optimization problem. And in some sense, this looks like a lot of math, but frankly, it's actually easy to come up with. The definition of the slack variable demanded that all the slacks should be positive. So we have a whole bunch of new constraints. All the slacks should be positive. We allowed some examples, we allowed every example the liberty of breaking into the margin by an amount equal to psi. So the distance between the separator and each example is not at least 1, but at least 1 minus psi I. But we don't want all examples to break into the margin. We want to put some control on how much slack we allow. So we add an extra term to the objective and say we are not going to allow, we are going to minimize the total slack that we afford. So let's revisit this SVM, and usually I say soft SVM here, but usually when people say SVM, this is what they mean. This is another optimization problem. It's also a quadratic program because the objective is a quadratic term. This time we are minimizing not just in W's but W and all the slacks. So it's just basically increased the size of our optimization problem such that every example should have a functional margin of at least 1 minus psi and all the slacks should be 0, should be positive. This is linear, this is quadratic. So we are still in this happy world of quadratic programming. In order to interpret this, now the way to think about it is we want to maximize the margin. That is the half W transpose W, that's what we started off with. That's going to remain with us forever. In addition, we are going to try to minimize the total slack. We want to allow as few examples to break into the margin as possible. There's a new term here called C. C is a trade-off parameter. It's a hyperparameter that we've now introduced. C is a trade-off between these two terms of how much do you want to allow the learner to overfit the data. Because if you want the learner to overfit the data, imagine C is very high. Imagine C is infinity. That means if C is infinity, that means in this objective, the second term has to be 0. That's the only way in which you can minimize this. If I set C to be infinity, then what I'm saying is I demand that the sum of size should be 0. We know that all the sides are positive. If I want to find a set of positive numbers that all add up to be 0, what is the only answer? All of them are 0, which means all the slacks have to be 0, which means all points have to be outside the margin. If C is infinity, then what I'm saying is I want to overfit the data. If C is 0, then I'm saying I don't care. Find anything, allow all the size to be infinity, allow every point to break into the margin, I don't care, just find me a way. In fact, if C is 0, then you are essentially saying there is a trivial answer by setting all the size to be infinity and setting the weights to 0. So C equals infinity implies overfit. C equals 0 implies what is called underfit. And this is a knob that we get to control to trade off how much we want to overfit the data, and we are going to find C by cross-validation. Before we move on, are there any questions? And I probably have not introduced the word underfit before. What I mean by that is I get a weight vector that does not adequately explain the data. If C equals 0, I get a 0 weight vector, which basically does not give me any way of labeling the data. Yes?
What is underfit?
That's what I was saying. Underfitting means Oh, so overfitting means I want to explain every example in the data. I want a classifier that explains every example. Underfitting means I'm willing to live with, I have a classifier that does not adequately explain the data. In particular, if C is 0, I get a weight vector that is 0. Because if C is 0, then I get a trivial solution by setting W equals 0 and psi equals infinity. That will be the minimizer. Right? Which means if W equals 0, I get a classifier whose weight vector is 0. Which means it will always predict plus for all future examples. So, not good. Underfitting basically says the learner is unable to adequately explain or label the data. We'll see this in multiple forms as we go on. It turns out there's actually a way to eliminate the slack variables completely from this optimization problem and rewrite it by noticing that psi I is greater than or equal to 0, and this, I can rewrite this as psi I is greater than or equal to 1 minus yi w transpose xi. Both of these should hold, right? This is this thing here becomes the first one, and the second one is, this is true for all I. If it is greater than 0 and greater than 1 minus y w transpose x, it means it should be greater than the bigger of these two things, right? I can summarize this together as that I is greater than max psi I is an upper bound for this quantity here, max w transpose 0 comma maximum of 1 minus y w transpose x. And not going to get too much into the details. Because we have an upper bound of this quantity, we can essentially replace the psi I in the objective with this term on the right hand side. What we'll get is the first term remains the same, the second term, the psi I, is replaced by max of 0 comma 1 minus y w transpose x. All the constraints are gone because the constraints are all folded into that single term. So this is an unconstrained optimization problem. And it turns out this version of the optimization problem is more interpretable. And let me explain. So there are two terms in this objective, and there are no constraints. The first term basically says, I want to find a classifier that maximizes the margin. More generally, the first term says, I want to find a classifier that generalizes better, because maximizing the margin gives you better generalization. This term, in general, is called the regularizer. The regularizer is a function of the parameters that pushes for generalization. The second term is the second term here is essentially saying I'm going to add up penalties for mispredicting over each example. So it's sum over all the training examples. We can, in order to interpret the second term, we should consider three cases. So first case is if the example is correctly classified and outside the margin. If the example is correctly classified, we know that y w transpose x is greater than 0. If it is correctly classified and outside the margin, let's put greater than equal to. If it's outside the margin, we know that it's not just greater than 0, but greater than 1. Which means 1 minus y w transpose x is greater than 0. It's less than 0. Right? Okay? That means the max of 0 and this term is 0. Now, if you interpret this as a penalty for misclassification, if for any class example in the training set that's correctly classified by a weight vector and is put outside the margin, the penalty is 0. You don't have to pay any penalty for putting a data point on the correct side of the margin. Now, if an example is classified incorrectly, then y w transpose x is less than 0, which means it's less than 1. Which means the max of y of 1 minus y w transpose x, 0 is equal to 1 minus y w transpose x, which is a positive number. What this is saying is if a particular weight vector classifies an example incorrectly, it's allowed to classify the example incorrectly, but it has to pay this much of a price in the optimization. It has to pay that price. That's the price of the ticket for misclassification. Now, this makes sense, right? I mean, if the example is classified correctly, there's no penalty. If the example is classified incorrectly, it has to pay some penalty. That's all fine. But what makes the whole thing interesting is SVM forces weight vectors to pay a penalty even if an example is classified correctly but is within the margin. So if y w transpose x is greater than 0 and y w transpose x is less than 1. That means this quantity here, max of 0, y 1 minus y w transpose x, is still 1 minus y w transpose x, a positive number. Because 1 minus y w transpose x, because of this term, will be positive. What this is saying is that even if a weight vector classifies an example correctly, but that example breaks into the margin, it still has to pay a penalty. And because we are minimizing over that quantity, we are trying to minimize the total penalty, so this will automatically try to find weight vectors that tries to classify, that prevent these two situations, that prevents examples from being misclassified and also tries to push examples away from the margin. That's what the SVM optimization does. Notice that I have described this whole thing without talking about any algorithm. This is true for any algorithm that minimizes that quantity. The quantity inside the box on top is called the hinge loss function. What we have now defined is a penalty for misclassification, essentially penalty for every example. Sometimes the penalty is 0. The hinge loss is a particular penalty function that takes the shape of max of 0, 1 minus y w transpose x. There's a way of interpreting this pictorially, if you prefer that. The hinge loss, hinge loss is defined to be max. I'll probably have that on the next slide. Yeah. Imagine that we want to penalize mistakes. Okay? And the way we are going to penalize mistakes is by looking at that quantity y w transpose x. That's the quantity on the horizontal axis. If you know from our perceptron days that a weight vector does not make a mistake if y w transpose x is positive. If y w transpose x is positive, the red line, what I have labeled as the 0-1 loss, makes acquires no penalty. On this, there is a penalty of 1. Essentially, the quantity that we would like to minimize. We want to add up all the 0-1 losses and minimize that because we want to minimize the number of mistakes. This is basically saying every time there's a mistake, you pay a price of 1. That's the quantity that we would like to minimize, but it turns out that's intractable. The hinge loss is actually a convex surrogate. What the hinge loss says, so this is the explanation of 0-1 loss. 0-1 loss says if the sign of y and w transpose x are the same, there's no penalty. If the signs are different, then there is a penalty. The hinge loss is a surrogate. It has 3 regions. So 1, 2, and here, let's call this ABC. Region A, there's no penalty. The value of the sign of YW transpose X is positive, and it is more than 1. So 1 is the margin here. It's outside the margin for a particular example X and Y. So in region A, there is no penalty, so the loss is 0. In region C, where the 0,1 loss acquires a penalty, the hinge loss acquires an increasing penalty as we go along, because it's increasing as putting an example here is worse than putting an example here. As you go farther away from the margin on the wrong side, you have to pay a higher and higher penalty, so it's better not to put examples farther away. The interesting part of the hinge loss is even in this region, where the 0,1 loss says you made the correct classification, the Y and W transpose X have the same sign in this region B, and yet the hinge loss pays a penalty. And the reason for that is it prefers putting examples in region A. It tries to find weight vectors so that examples are in region A. So those are the 3 cases for the hinge loss, and this gives us, I'm going to just wind up this lecture with generalization of this principle, and I'm going to pick this up again at the end of tomorrow's, at the latter half of Tuesday's lecture as well. There's a general learning principle here called the principle of minimizing risk. What we do is for any classifier, in this case it's a linear separator, but you can think of 15-layer neural networks, for example. We define the notion of a loss. The loss is the penalty that is paid when the classifier makes a mistake. And then we can define learning as minimizing loss, finding the classifier, finding the hypothesis that has the lowest cumulative loss on the training set. This is the principle of risk minimization. SVMs have what is called regularized risk minimization. In addition to the loss that is essentially an error, a cumulative error on the training example, we also have another term. In this case, for the SVM, it was the W transpose W term, that tries to push classifiers towards low complexity. Remember, how did we come to W transpose W? Minimizing W transpose W is pushing towards maximum margin. Maximum margin is equivalent to lower VC dimension. Lower VC dimension generalizes better because it is called it's a smaller hypothesis class. So there is another term called the regularizer, which penalizes complexity. Minimizing W transpose W is essentially penalizing complexity, and I like to think of this as capacity control. We want to control the capacity of our classifiers so that they are not overly expressive. So regularized risk minimization trades off between 2 terms. I want to find a classifier that has the lowest regularizer plus loss. And last thing I want to do today is to just walk you through the three parts of the SVM objectives. There's the regularization term, the first term, that says maximize the margin. It imposes a preference for less complex hypothesis spaces, and it turns out you can replace this with other regularizers also, and they give you different kinds of guarantees. The second term is the empirical loss. In this case, the SVM uses what's called the hinge loss, this quantity here. It penalizes weight vectors when they make mistakes, and it turns out you can replace the hinge loss with other losses also. Different loss functions give you different named classifiers. As an example, the perceptron algorithm that we all know and love is a particular instance of this framework where this quantity does not exist, and this is replaced with something called the perceptron loss, and I'll get to that later. In SVM, the regularization and empirical loss. So this pushes for overfitting, and this pushes for generalization. These two aspects can be traded off against each other with this single hyperparameter C that controls the trade-off between large margin and small loss. And both these terms, the regularizer and the loss, can be swapped out with other regularizers or other loss to give us other named algorithms. A popular example of that is the logistic regression. Alright, I'm going to stop now because I'm a minute over time. Just a reminder of announcements, there's a homework. Please continue doing all the good work you're doing with your projects, and there's a talk tomorrow.